In video number 138, I talked about key features of power supplies. Besides safety, typical performance characteristics like supply current and short-circuit behavior are most important. Today, I am testing some of my DC power supplies to find out how useful they are to power a digital model railroad. Hello everyone and welcome to the IoTT channel. I am Hans Tanner. A special welcome to all new subscribers and welcome back to everyone else. I'm happy you made it here and thank you for your support of my channel. And if you are not yet a subscriber, it's a good idea to click the subscribe button and activate the notification function so that you are always in a premium seat when new videos come out. Yes, that is correct. It makes a difference whether you are powering an analog or a digital model railroad, either a digital command station or a digital booster. There are fundamental differences between analog and digital track power when it comes to how to handle a short-circuit situation. So what I will do in this video is have a look at the differences between analog and digital systems when it comes to handling a short circuit. This may be a little bit basic for some of you, so feel free to skip ahead. Then I will explain my test setup to measure the short circuit current without creating damage to the power supply or the power electronics. And finally, I will measure the short circuit current of some typical power supplies and try to conclude if they may be a good fit to power a digital command station or booster. So let's get started and compare the principal schematics of the two system types, starting with an analog system. Analog systems are working either with DC or AC, and they essentially work by controlling the locomotive speed and direction by modifying the track voltage and, in the case of DC systems, the track polarity. The basic configuration is simple. It starts with a transformer that converts the line voltage to a lower level that cannot cause harm to the user when touching the wires or track. The transformer in the most simple systems is regulated, meaning there is a knob to control the output voltage. The AC output is then rectified to DC and passed through a polarity switch to reverse the output polarity. All these components are usually integrated into one single box, commonly called transformer or train control unit or the like. Track feeder wires are then connected to the output of that box, and the current is sent via wires and the rails to the wheel pickup of the locomotive and then to the motor inside of the locomotive. There are some common variations to the basic concept. Instead of using a regulated output transformer, one with a fixed output voltage can be used. In this case, the output voltage is then fed through an electronic regulator to control the final output voltage. The same principal configuration can also be used for AC systems. In this case, there is no need for a rectifier, but the transformer can output an overvoltage pulse, which then triggers a relay inside the locomotive that activates a direction reversal switch to change the travel direction. As mentioned in the relatively recent NMRA technical note TN9, all these transformer setups for analog model railroads have in common that they are usually used to power just one block with one train, and if there are several blocks on a larger layout, they are typically powered by separate transformers. In case of a short circuit in the track wiring or on the track itself, for example because a train is derailing and creates a bridge between the two rails, the effect is the same for all of these analog systems. The short circuit creates a bypass of the locomotive motor for the current. As a result, the resistance of the entire loop becomes much lower and the current increases. It is in fact only limited by the output voltage of the transformer divided by the total resistance in the entire track and wire loop, so the remaining rails, the feeder wires, and the internal resistance of the control device. The resulting current can be a multitude of the current amount that is flowing when the locomotive is running normally. This current flow can pump a lot of energy into the system, which can result in damages if the short circuit is not removed. Typical results could be some thin wires heating up or some wheels welded to the track. To prevent that from happening, there needs to be a weak link somewhere in the circuit. A weak link means something that is intended to break if the current reaches values that can cause harm, so something like a fuse or a circuit breaker. The way it works is simple. If the current is higher than the current expected during regular use, the fuse starts to heat up, and if the situation persists, the wire inside the fuse will melt from the heat that is generated, and the circuit is interrupted. The reaction time is rather slow, and there are different types of fuses from slow blow to super fast blow. They all have in common that they will break at the given current, but the time it takes is different depending on the blow type. What is important with fuses for analog systems is that the power supply can deliver enough current to make the fuse blow. Here are some typical blow curves of fuses. As you can see, to make it blow quickly, the short circuit current needs to be quite high. To blow a 5 amp fuse in 5 seconds, you need about 13 amps. A current flow of 10 amps will make it blow in about 30 seconds. That is rather a long time, and that is why the DC power stations usually have a built-in overcurrent protection that reacts faster, usually by just limiting the current to an amount slightly above the nominal output current. There is an additional category of analog systems, and that is PWM control stations. PWM stands for pulse width modulation, and what it does is sending out short pulses of a constant voltage to the track. So the voltage is always the same, but the time it is switched on is proportional to the speed the train should go. This on ratio is called the duty cycle, and it can vary between 0 and 100%. The effect on the motor is the same as if the voltage would gradually change, so it behaves like an analog system, even though the track voltage is sort of digital, either on or off. This track power switching is generated by an electronic switch, basically the same mechanism as in a digital command control system. Therefore, when it comes to the behavior under short circuit, such systems are comparable to digital command control systems, so what we are going to look at next largely applies for PWM systems as well. So here are the schematics of a digital command control system. A transformer with fixed voltage output followed by a rectifier to create a DC voltage. Those two components can be integrated into a so-called DC power supply, as we will see in a minute. The DC output is then fed into the H-bridge, which is a specialized switch to control the voltage and polarity at the output of the command station. The H-bridge really is the heart of the system, so let me quickly explain how it works. Here is the internal schematics of an H-bridge, basically an arrangement of 4 transistors along with some control circuits. The 4 transistors can be used to connect each of the 2 outputs to either positive or negative supply voltage. If transistors 1 and 3 are on, output 1 has supply voltage and output 2 carries ground. If transistors 2 and 4 are on, the polarity of outputs 1 and 2 is reversed. Output 1 has ground and output 2 carries the supply voltage. So the output only depends on how the transistors are switched on or off, and this is typically controlled by the microcontroller in the system. To generate the PWM output, typically transistor 3 is on and transistor 1 is switched on and off to output the desired duty cycle for a forward movement. Then, to reverse the polarity and make the train move backwards, transistor 4 is on permanently and transistor 2 is used to create the duty cycle. For DCC, all that changes is the sequence of how the transistors are controlled. Instead of just turning one of them on and off to create a PWM output, all 4 of them are used to create the polarity changing DCC signal. So for a 1-bit, transistor 1 and 3 are turned on for 58 microseconds, then transistors 2 and 4 are turned on for the same amount of time to create the second half of the bit. Then the process starts again for the next bit. So the output is essentially an AC with a rectangular waveform. Now, when it comes to a short circuit, things are different compared to the analog systems we covered before, as the transistors are much more sensitive to high currents compared to relatively insensitive wires and the like. If a short circuit happens and the current through the H-bridge multiplies, it will burn much faster than a typical fuse. To prevent damage, the microcontroller therefore must monitor the current through the H-bridge on a regular basis and shut it down relatively fast if the maximum allowed current through the device is exceeded. What relatively fast exactly means is defined in the software of the command station. In the case of the DCC-X command station, the time a short circuit must be active until the track is shut down is a little over 100 milliseconds, as we can see in this oscillo screenshot. The red line is the power pin that enables the H-bridge. The blue line shows the analog input. If a short circuit occurs, the analog input goes up as the current increases. If analog is still high about 100 milliseconds later, the power line goes low to shut down the track output. Other command stations and boosters appear to use about the same or even longer delays. Here are the screenshots from a Digitrax DCS100 command station and the Digitrax DB100 booster. The DCS100 shuts the track power after about 130 milliseconds, while the DB100 booster takes about twice that long. An interesting exception I found was the Digitrax DB99 booster, which does not shut down at all, but apparently reduces the output current to about 1.5 amps until the short circuit goes away. So to make short circuit protection work, 2 conditions must be met. The short circuit must be constantly on during the detection time. If the short circuit is very brief or not permanently drawing enough current, it is not detected. And second, the power supply must be able to deliver a high enough current to maintain the short circuit condition for the time until shutdown. This second condition is potentially problematic. If the power supply has an internal protection that is faster than 100 milliseconds, it may shut the power to the command station before the command station detects the short circuit condition. Such a situation is shown in this screenshot. The power supply was loaded very close to the nominal current when a short circuit occurred. It took about 20 milliseconds until the internal protection of the power supply was triggered and the power to the command station shut. Why is this a problem? After all, the power was shut, so the protection worked. Well, it is a problem if you are using one of these 2 configurations. First, you use one single power supply to supply power to 2 track outputs, as is the case when using a standard Arduino motor shield, the DCC-X motor shield, or when powering 2 IoTT power shields from the same power supply. In this case, a short circuit on one output that causes the power supply to shut down will also take out the second output. Another example is if you are powering a command station and a booster from the same power supply. And the second situation is if you are powering the Arduino board of a DCC-X command station from the main power supply input as it is possible with the DC-DC converter on the DCC-X motor shield or with the IoTT DCC aux shield. The problem here is that if a short circuit occurs and the DC supply shuts down, the command station is going through a reboot process and you might lose the runtime data. If you are using one of these configurations, it is therefore extremely important that the available short circuit current of the DC power supply can exceed the trip current for the entire 100 millisecond interval. My concern was in particular that this might not always be the case if the DC power supply is heavily loaded at the time the short circuit occurs, and that's what I tried to find out. So I set up a bunch of power resistors to simulate the regular track load and added a silverhead booster to measure the short circuit current. The silverhead has a built-in function to do exactly that, and it returns the short circuit current in milliamps at about 1, 50, 100 and 140 milliseconds after triggering a short circuit. Here is the setup I used for doing the measurements. From the power supply output I ran the positive wire through the amp meter and then to the resistor pack and back to the negative output of the power supply. My power resistors are nominally 1 ohm, but in reality they are more like 1.3 ohms. I used up to 7 of them in series to achieve a current that is around 90% of the nominal output of each power supply I wanted to test. So for a 5 amp power supply I would select the number of resistors so that the current would be in the area of about 4.5 to 4.8 amps. Using ohmic resistors is, by the way, pretty much the worst case scenario to load a digital command station, as the ohmic resistor causes a continuous current flow the entire time. This is much more demanding for the power supply than a locomotive load, which is normally just a series of brief pulses, as the decoder also uses a PWM pulse to drive the motor. Next, I wired the DC supply output to the input of the power shield of the silverhead booster, and on the DCC output side of the booster I put the wire bridge simulating a short circuit on the track. The silverhead function to measure the track short circuit current and display it is included in the silverhead web page. All you need to do is to click the measurement button, which shuts down the track power and brings up the dialog to trigger the test. You now can apply a short circuit while the track is unpowered. When done, you click the Start Test button. The silverhead applies the track power for about 150 milliseconds and measures the current that is flowing through the power shield. The H-bridge can handle up to 43 amps, so this can be done without risk to the H-bridge. The measurement circuit can measure up to about 11.5 amps, and the result is displayed on screen in milliamps. So with this setup, it is possible to preload the power supply to the track current that represents the drain operation and then apply a short circuit on top of it, just as if a train operating on the full load would derail. The target current I am looking for is at least about 10% higher than the trip current I plan to use on the command station or booster, and maintained for the entire short circuit measurement time of about 150 milliseconds. This will make sure that in case of a short circuit, the booster always will shut down the track before any protection mechanism of the power supply gets triggered. Here are the power supplies I used in this test. I started with my lab power supply, which I have tested before, and I know that it can deliver plenty of short circuit current under all circumstances. I basically used it to verify the test setup. Next, I tested a 12 volt 1.5 amp wall-wart type DC supply that I have kept from a no longer used TP-Link router. This is certainly at the very low end for model railroading, but for a small N-scale layout or for powering a separate system to run a programming track, it might be a possible solution. Then I had a look at 4 old notebook power supplies. The first one was a 15 volt 4 amp Toshiba. That one is from 2001, so more than 20 years old. The other 3 were all around 19 volts output, but different nominal current. The first, from Asus, can deliver 3.4 amps at 19 volts. The second is from HP and outputs maximal 3.3 amps at 19.5 volts. And the third, from Dell, can provide 4.6 amps at 19.5 volts, but is slightly bigger. And finally, I measured the short current of my 12 volt 30 amp open frame switching power supply. Of course, as recommended in video number 138, I put it in a plastic enclosure for safety reasons because of the readily accessible connector block. The tests were pretty uneventful. In the first run, I tested the short circuit current of each power supply without preload. All of them showed a short circuit current maxing out the measurement range of the power shield, which is in the area of 11.8 amps. Then I repeated the measurement series with each power supply preloaded to about 90% of the nominal current. Of course, the preloading is not very precise, as I had to put the power resistors in a serial and parallel combination to come as close as possible to the desired current value. And to make things worse, the resistors were warming up significantly during the test, so it was a bit of a moving target. Anyway, the pre-test current column in this table shows the amp meter reading right at the time when I triggered the short circuit test. As we can see, with the exception of the Walmart type TP-Link power supply, all power supplies could deliver roughly the same short circuit current on top of the regular load. That was actually much better than what I expected. The TP-Link, on the other hand, shut down before the 50 millisecond measurement took place, even though the initial short circuit current was higher than the measurement range of the power shield, but it could not be sustained. While doing the tests, I noticed a very interesting behavior of the notebook power supplies. When I lowered the load resistance, the current would increase as expected. But then the power supplies actually started to scale down the output voltage in a way that the output wattage did not exceed the nominal output wattage, even though the current was higher than the nominal current. So these power supplies, when overloaded, do not immediately shut down, but first try to reduce the output voltage so that the product of output voltage and output amps remains constant. When I saw that, I could not resist to repeat the test with a starting current that was higher than the nominal output current. So I hooked up the Dell power supply and preloaded it with 5 amps, which is about 10% more than the nominal current of 4.62 amps. When I ran the short circuit test, it shut down before the second reading at around 50 milliseconds as seen here. It actually then remained off for probably about 2 minutes with 0 volts output voltage, long enough indeed to make me think I had killed it. But then it came back and worked as before. But in the interest of the lifespan of my power supplies, I did not repeat the test with overloaded initial output for the other ones. So what are the insights, conclusions and recommendations from this test? Well, using small power supplies with less than say 3 amps nominal output is not really recommended. The main reason is that for these small devices, the short circuit peak current is over proportionally high compared to the nominal output, and the risk that they shut down before the command station does is significantly higher than with the higher output DC supplies. Then, to be on the safe side, the normal current load during regular operation should not exceed, say, 90% of the nominal output current. This makes sure that the power supply can provide enough short circuit current for long enough so that the command station can shut down before the DC supply does. And when supplying more than one track output from one single power supply, it should be capable to output enough power to supply all connected districts and still have enough reserve for handling a short circuit in one of the districts. Of course, during normal operation, not all districts are loaded all the time, so the output current can be less than the sum of all district currents. How much less depends on the way how you operate your layout, but I would think that about 50% would be a meaningful starting point. If you supply, say, 4 5-amp districts from one power supply, a nominal current of 10 amps would probably be what I'm looking for. It might also be a good idea to add a circuit breaker before the boosters and command station to protect the wiring between the power supply and the boosters, as it is recommended, for example, by Digitrax when supplying 2 boosters from the same PS2012E power supply. One topic I have not covered in this video is circuit breakers downstream from the command station or booster. It is quite common to split the output from a command station to supply several block sections. If they remain unprotected, a short circuit in one block section will shut down all of them together as the track output is shut. To avoid that, it is possible to add individual breakers in each section feeder so that the section can shut down without taking out all the other sections while the booster remains on. The key criteria to make this work is that the section breakers react faster than the 100 milliseconds delay time of the command station or main booster, so say in 50 or 60 milliseconds, so that the booster protection does not get triggered. So it is not so much a question of the current limit, but more a question of reaction time. Personally, I have no experience yet with such devices. If you do, please leave a comment in the comment section of this video. If there is enough interest, I may investigate such devices in a future video. And that's it for today. I hope this information was useful or at least interesting for you, and it helps you to power your layouts safely and reliably. If you like this kind of information, please click the like button below to let me know. It is free and only takes a second, but it helps a great deal to promote the IoTT channel and trigger YouTube to let other model railroaders know about these videos, because YouTube likes the likes. Thanks for watching and see you in the next video.